Okay, so hello everyone. In this video, we'll be looking at an exercise where we try to show that a language is not regular. So in this case, the language we're trying to show isn't regular is the language that contains strings which look like A's and then B's, where the number of B's is greater than the number of A's, the number of A's is even, and the number of B's is odd, right? And so intuitively, this is not regular because of this condition, right? These two conditions are very easy to recognize using a DFA. It's this condition that's a bit trickier, and that's actually impossible to use a DFA for because, intuitively, this kind of requires memory, right? So this kind of requires uh, some kind of memory here because you have to sort of remember how many A's you've seen and then check that the number of B's you see is greater than that. And because, right, the number of A's can grow arbitrarily large, if you wanted to use something like a finite state machine for this, you would have to encode every single possible length of A, right? Um, and that would, very quickly become an infinite machine, right? And that's not permissible when you're trying to show that a language is regular, designing a DFA, right? Because you have to have a finite number of states. But this is kind of like the intuition. So intu, intuitively, this is because this condition requires memory, right? You have to encode you have to remember how many A's you've seen. And so if you wanted to translate this to DFA, then you'd have to encode all the possible values for the numbers of A's, and that would blow up. But this is an intuitive argument, right? So what we actually need to do is we need to provide like a formal argument. So we can either use the pumping lemma, or we can use closure properties. I mean, actually, we can also use the Myhill-Néraud theorem to prove that this language is not regular, but um, I'm not going to do the Myhill-Néraud theorem in this video. And closure properties here, um, yeah, it might be tricky to use closure properties here. So instead, I'm just going to argue directly by using the pumping lemma. Okay. And so just as a reminder, how do I use the pumping lemma to show that something is not regular? You can think of it as kind of like playing a game, right? So playing a game. Between uh, you and an opponent, right? Where the opponent is the for all quantifier, and you where the opponent plays the for all quantifier and you play uh, the existential quantifier. So why are we talking about playing, right? Just as a reminder, because what the pumping lemma states is that there is some pumping length. There is some pumping length. Well, okay, it says that if L is regular, then there is some pumping length such that for every string in L, uh, of size greater or equal to P, there exists some decomposition of W, X, Y, Z, where XY is at most P and Y is at least 1. So there's this kind of decomposition where for every I uh, in, so here, let's see. Yeah, here I'm actually going to have to say that the natural numbers here include 0. Okay, where for any I, including 0, um, when you pump up or down the middle part of this decomposition, you still remain in the language L, right? And so this is like, if the language is regular, then this is true. So how do I use the pumping lemma to show that a language is not regular? Well, I can use the contrapositive, right? So I can say, if this is not true, then, so let's say if this is not true, so if this is false, then it implies that this is false, right? I'm just using the contrapositive. So meaning that what I want to show, so what I want to show um, is that for every pumping length that you pick, you can find some string L where the length, some string W where the length of that string is greater or equal to P, where regardless of the decomposition, if it follows these rules, you can find a pumping length, right? Regardless of the decomposition for this string W, you can find a pumping length such that when you pump with that pumping length, you get a string that's not in L, right? And so, right, I need to show, given this language L, that I can satisfy this statement, right? So I want to show uh, this statement uh, using where L is equal to the language that I want to show is not regular. So um, where L is this language. Ah, okay. So I can just do this. Where L is this, right? Okay, well, to do this, like I said, to sort of satisfy this statement, you can kind of think about it as a game, which is what I was kind of talking about here. So essentially, you're going to play a game where the point of the game is, of course, to win. The opponent is going to play the for all, and your goal is to play that there exists and to defeat the opponent. So what's the strategy here? Your opponent picks some number. You have no control over what they pick. It's just some number, some natural number P. You pick a particular string W that has to, because you want to follow the rules of the game, that has to have length at least P. Then your opponent picks some decomposition. You can't control what the decomposition is. What you can control, though, is what I you pick to get the pumped string not in L. And so the whole crux actually of the pumping lemma is kind of doing a bit of chess and predicting the kind of future by saying, well, what's a good W where no matter what the decomposition my opponent picked would be, I would be able to get an I which for which X, Y, I, Z is not in L. So you're kind of like doing a bit of forward thinking, right? And so that's going to be my approach here, right? So how am I going to do this? So let's like I said, do this as a game. So it's first it's the for all players turn. So the for all player just picks some natural number P, right? You have no control over what P is. So um, you don't know, and can't control what P is. Okay. Now the goal at this point is to select a string that is an L, right? So that does satisfy these conditions, where if you think sort of a bit in the future, you're going to be able to find some kind of pump, um, some kind of I, where when you pump with that I, you're going to sort of go outside of the language L. So let's see. I mean, there are a few options, right? One option that someone might start with is I know that the string has to have length at least P. So then you might pick something like W is AP, right? I mean, now the length of W is definitely greater or equal to P. But this doesn't work because actually this string doesn't satisfy the conditions here, so it's not even an L, right? But W is not an L, so that's not going to work. Okay, so how do I satisfy the conditions in L? Well, I definitely need M, so the number of B's to be greater than the number of A's. Okay, so let's just say that I have one more B's than I have A's. So uh, let's say the string W is AP BP plus 1. So again, the length of W is, in this case, 2P plus 1, which is definitely greater or equal to P. And now in this case, P plus 1 is strictly greater than P. But there is this other condition, right? Where the number of A's is even and the number of B's is odd. And there's actually no guarantee that P here is even and P plus 1 is odd because you have no control over what your opponent picked, right? And so this is kind of why we emphasize this playing a game strategy because it helps you remember that you have no control over what the for all player is doing, right? So this is also not valid because it's very feasible that your for all player just out of random chance picked P as being odd, in which case this would be odd and this would be even. So this would not be in the language W. So, but the for all could pick P, uh, what did I say? P odd, in which case they would like defeat you immediately, in which case you lose uh, immediately. Okay, so that's not going to work. But I can kind of force, based on any natural number P, I can actually ensure that I have an even and a non number. How do I do that? Well, for even, I multiply the number by 2. For odd, I multiply by 2, add 1. And that's, I think, going to probably work out, right? So W is A2P, B 2P plus 1. So now the length of the string W is 4P plus 1, which is greater or equal to P. So the number of B's is 2P plus 1, and that's strictly greater than 2P. And in this case, the number of A's is even, and the number of B's is odd, right? So that's also respecting. So then I do have a string W that, regardless of what the for all player picked, is an L. So then this is an L, right? Okay, nice. And now it's the for all player's turn again. So now it's the for all player, and the for all player, what they're going to do in this at this part of at this stage of the game is they're going to decompose the string. But you have no control over what the decomposition looks like. You only know that they have to respect certain rules. And so the rules of decomposition are that the length of y has to be greater or equal to 1, and the length of xy has to be at most p. So what does this tell you about what the decomposition kind of looks like? If I represent W a bit more explicitly, so I have something like this. So I know that I have like 2P A's here and 2P plus 1 B's here. Then because the decomposition has to be um, sort of because this is equal to X, Y, Z, then it has to be that like X is kind of the first part of the string, Y is the second part, and Z is the third part. And because I have two PAs, and I know that X concat with Y has that length at most P, then XY can reach at most position P, right? So position 1 all the way to P. So XY, right? Uh, what this is telling me is XY looks like some number of A's, so A power K. And the y's, the y, right? The y here is also some number of a's, right? And it's in particular some number of a's, at least one a. So it's the y is some number of a's, um, where that number is at least one because of this condition. So we know this, where k is at most p. And we also know, right, so xy is a k. And we also know that y is, let's say, at, where t is at least one. And also because um, concatenated with x, uh, xy is of length at most p, then y also has to have length at most p, right? Because if it had length greater than p, then if you concatenate a string of length greater than p with any other string, then that resulting string has length greater than p, right? And then that sort of defies this rule. So then I also need this to be true. Um, and just like a note, it's very possible that x could be the empty string, right? Maybe it's not. You have no control over what x is. You can't tell your opponent what to do, but it's possible that they pick x as the empty string. And so that means that z, in this case, z is just the remainder, the remaining number of a's. So it's like a to p minus k, and then all the b's, b to p plus 1. Okay. And that's the decomposition, right? So now it's my turn, right? Now it's my turn. So at my turn, I basically need to pick an I in N where, remember, I could be 0. Uh, right. Such that, such that, X, Y, I, Z is not in L. So in other words, if I take the part that is Y, and maybe I like select, so for instance, if I select I as 2, then the resulting string I'll call W sub 2 is X, Y, Y, Z, right? Because Y squared is just Y, Y. Then what this means is that W2 is like, you have Y somewhere here, then it's like injecting an extra copy of Y there, right? So you're adding an additional TAs to your string, okay? Okay, so how can I pick, what I can I pick such that when I inject, or also if I remove, right? Because if I pick I as 0, then I'm actually taking away that y. So if I remove or inject an extra y, then how can I not be in L? So let's see. I need to essentially think, how can I break the conditions here? Well, I think the simplest thing, right, is to break maybe this condition, right? So I can easily break the condition that um, the number of A's here is strictly less than the number of B's. How can I do that? Well, let me just inject an extra Y. If I inject an extra Y, I know that the Y has length at least 1, so there's at least one A in there because of this condition. Um, and so if I inject a string that has at least one symbol, then I'll get 2p plus at least 1. And then it's definitely no longer true that one is strictly less than the other. So that seems to be a good strategy. So if I pick I is equal to, so actually, instead of just saying EG, let's just pick I is equal to 2. So I get W2 is X, Y, Y, Z. So in fact, that means that W2 is A to P plus T, right? Because I'm adding an extra Y here. B to P plus 1. And so now I can just argue very easily that this is not an L. So this works because 2p plus 1 plus t, sorry, is greater or equal to 2p plus 1 because t is greater or equal to 1. And so this implies that the number of a's is no longer strictly less than the number of b's. So therefore, W2 is not in L because its first condition is not satisfied. Okay. And this kind of completes actually the pumping lemma proof because I've managed to satisfy this statement, right? I've like shown that I've allowed my opponent to pick an arbitrary P, then I select a particular W, I've allowed them to pick an arbitrary decomposition, and I've selected an I where I've shown that with that I get a string that's not an L. So that means that this statement is satisfied, which means that this statement, L is not regular, will also be satisfied. So therefore, L is not regular. Um, and this concludes the proof, right? So as an exercise for you, maybe though, if I picked I is equal to 0, would this still hold? This argument still work? Okay, this is something for you. Okay, great. So thanks a lot, and yeah, see you in the next one.